adding more and more layers and different kinds of layers. And this has made great progress, but in a certain way we're reaching a kind of a plateau. We're not, it doesn't look like this is the way to get to general artificial intelligence. For example, the way the brain does visual processing is there are 32 plus areas in primate visual cortex. Again, there's a lot of boxes and lines, but I would argue that the processing is quite different. That each of these areas has local recurrence and microcircuits within them, and the areas amongst themselves have a lot of recurrence. And deep learning often focuses on one particular stream, which is the what stream, the ventral stream in human vision. But actually there are multiple streams. There's where stream that looks at motion and color, and there's eye movement control, and there's emotional processing. A lot of other things go on. And just looking at two areas, primary visual cortex, V1 and V1 and V2. V1 is where input comes first, and then it proceeds on to V2 and V4 and on, at least in the ventral stream. And even between these two areas, there's actually a lot of recurrence. This is a vast simplification of what actually is happening. And even within the areas, there's recurrence between layers. There are 6 layers in most cortical areas. So it's a bit more complex than what we see in. So just for example, I can't see this very well, but some of my work was looking at pathways for threat detection, visual pathways for threat detection, and there's at least 5 just for that. So there are challenges in supervised deep learning. It's good at perception of images, but most of the data is actually unlabeled in the world, and it does have trouble with novel input. It has trouble with occluded objects. It can be fooled with adversarial data. The dynamics is quite limited compared to what human beings can do. And tension, you can do some tension processing by masking, but not like what we can do. And of course, there's no causal reasoning or common sense. Reinforcement learning, it's somewhere between unsupervised learning and supervised learning. In reinforcement learning, you have a reward value that tells you how good your prediction is. The problem with that is it can give you very low information compared to, let's say, supervised learning. So it can take many, many trials. And the real world does not really provide that many trials. You could also argue that things like ethics are going to require something more than reward, let's say in robotics, for example. But reinforcement learning can be combined with unsupervised learning just as it can be combined with supervised learning. Supervised learning can also be combined with unsupervised learning. So some recent observations, Jeffrey Hinton, one of the inventors of backpropagation, he's saying that for AI research to material continue, we need to throw away it all and start again. That's a pretty bold comment there. And Jan LeCun, who invented one of the inventors of convolutional networks, he's saying the revolution will not be supervised. And Josh Tannenbaum at MIT is doing work on toddlers and infant cognition, and he's saying that focusing on the human mind is a valuable way to achieve and to advance AI. So how do toddlers actually learn? I would argue that most of what toddlers do is unsupervised or reinforcement learning. We don't teach toddlers how to see. They learn to see. What we do is we tell them what the labels are. What is it they're seeing? How is it associated with other things? They themselves experience pleasure and pain. We teach them we can give them attention and other emotional feedback. They learn to crawl themselves, they observe sequences and they imitate them. They can learn things just by observing it once or twice. They can build models and play with the world, and they can learn social interactions, and self-awareness is also something that teaches them. So how do the brain circuits do this? I'm going to talk about heavy learning and specific neural tractor networks, how that's as an implementation of heavy learning. First, heavy in theory. Donald Hebb wrote a book, Organization of Behavior, in 1949, and he postulated these three postulates that have been quite influential in neuroscience. They have synapse between two neurons when an axon of cell A is near enough to excite a cell B and repeatedly persistently take part in firing it. Some growth process or metabolic change takes place in one or both cells such that A's efficiency as one cell's firing B is increased. So if one cell fires in conjunction with another, the synapse can strengthen. The cell assembly, a group of neurons tend to fire together to form a cell assembly. They build microcircuits. Those activity can persist after triggering events. So you stimulate part of it, and the whole assembly can become active. In phase sequences, perception, motor, thought processes entail sequential activation of sets assembly. So if there's overlapping cell assemblies, one can cause another to fire, cause another to fire, another to fire. And this is often paraphrased as neurons that fire together, wired together. But what wasn't included in the theory was that synapse also weaken when the neurons don't fire together. And actually, the cell assemblies can inhibit each other. There's mutual inhibition and compete. So what are neural tractor networks? A neural tractor is kind of it's a non-linear dynamical system from dynamical systems theory. It can define a surface where the dynamics can go into a surface with lower energy, for example. For example here, but it can actually happen in the neocortex. It can happen at many scales. It can represent the dynamics of neural assemblies, and it can be used to simulate how possible hypothesized neural microcircuits work. It can be nested and overlapping. I mean, you can have a microcircuit in a small piece of cortex that can act as an attractor, and you can have attractors within attractors within attractors. And one theory goes that the whole brain can activate it as an attractor, as global ignition, and that may represent a conscious event when it's active globally. But even beyond individuals, you can have social attractors. Conversation, opinion dynamics is also a kind of attractor. So these attractors can represent perception, processing, memory, and cognitive processes. And an idealized example of a neural attractor is the Hopfield model, which has been influential. And here, in this case, you have a couple of stored patterns. This can be images, it can be arbitrary patterns, and you can, at batch, you can compute the weights together, and then you can present a small part of that, and by seeking minimum energy of the network, it will converge to one of the stored memory patterns. And this can be done at batch, but also can be done incrementally. Adding new training can be done that way. Talking about the neocortex for a minute. The neocortex, it's kind of a nested kind of architecture of columns across cortex. There are mini columns, which are about 30 nanometers wide. They occur during development. As we age, some neurons die, but once you've learned, there is some redundancy, so you can retain memories. These can be contained in hypercolumns, sometimes up to 100 minicolumns. In visual cortex, they're often called hypercolumns. In other areas of cortex, they're often called macrocolumns. And sometimes you can see borders of these columns, but sometimes, like in association cortex, you cannot. So it's not clear where the borders are. Within these columns, you can have microcircuits, canonical microcircuits, and then some have been defined. Often, layer 2, 3 has a set of excitatory parameter cells, as does layer 5, 6, and then there's inhibitory cells which allow these populations to inhibit other populations and also regulate. Actually, it gets much more complicated. There's many cell types in the neocortex, and this is an abstraction also. So a challenge of computational neuroscientists is to find a microcircuit that is abstract and yet can actually inform on how behavior works. Some work at KTH and other places have looked at combining, modeling these mini columns and connections between mini columns, and this was further expanded into across these macro columns. And other people have also defined these basically memories across hypercolumns, including Rinkus and Menta. This is some example microcircuits that I used in my research, trying different variations and seeing what the behavior is. This shows at 3 scales. This is sort of at the mini column level, this is at the macro column level, and this is at the patch level, sort of like where the human connectome is. So it's possible to build models of multiple areas and then run simulations and see what the behavior is like. On top of these, you store the attractor memories, which is unsupervised learning. The attractors are learned, and they're often called sparse distributed memory, sparse distributed representations. The mentor calls them sparse distributed representations. And they encode the neuroassemblies, and they're connected with long-range connections, excitatory, or they can also inhibit if one pyramidal cell, for example, excites a interneuron, an inhibitory cell, it can then excites that, it can inhibit another pyramidal cell. So when these are partially activated, the attractor memories can complete and also compete with other attractor memories. This is an example simulation of a attention experiment where these are 2 cortical patches, and this bottom one is being stimulated, and it activates an attractor memory, it completes, and then there's projections to the let's say a different patch, for example V1 and V2, that then activates a different memory, sort of like which you might have in a hierarchy. So I want to mention something about backward masking. Backward masking is a technique used in psychophysics to understand human perception and the timing of it. Often the way the experiments work is you present some image or target and then a mask. And the mask is, let's say if it's 25 microseconds after the target, it can block that target and it may be subliminal. If it's longer, the subject may see it. And you can use computation, you can test this kind of thing against computational models as well. I did this with one model. This is a model of V1 and V2. This is part of cortex with across the layers. And here, this is just the target being stimulated, and there's a completion of the patterns across with just a target and no mask. When a mask is presented, it blocks the activation of the target until the interval called the SOA between the presentation of the target and the mask increases until at some point there's enough time that the recurrence within the network can activate other neurons and then cause the pattern to complete. It also propagates forward to, let's say, V2, and that activation can propagate back and reinforce activation of a particular feature detector, for example. Here you see the simulation ran with feedback connections and without feedback connections. And with feedback connections, it was more likely to become active and propagate forward, so more likely to become conscious. This is a paper I just discovered. Actually, it came out last month. And what they did is they took, they took AlexNet and they extended it. If it ran normal feed forward, they extended it and they added a Hopfield network in one of the fully connected layers. So what they've done is they kind of merged a little bit of unsupervised and supervised learning into a deep learning network, which I think is kind of interesting. And what you're seeing here is that the outlined circles are the stored memories, and the full circles are occluded images that they're presenting to the network. And when they iterate, what it's doing is the occluded images are like the attractor I showed you. They're Hopfield network. They're converging on one of the full saved memories. So this is and they've been able to do better. I mean, that normally the deep learning networks don't do well, and they've made some interesting progress on that. When you talk about unsupervised learning, you're basically coming up with clusters, and then what the problem is how do you label these clusters? There's been some success in that. For example, in natural language processing, when you do topic modeling, you have to, that's unsupervised, and you have to be able to name a topic, for example. And there's certain ways of doing that. So it's doable, but this is an important problem, I think, with unsupervised learning, is to figure out how do we label them, how are they related to other classes that are emerging, what's relevant, and if we can label them, then we can also possibly link to symbolic computation as well. Once you have them labeled, then also the question is, you have all these patterns coming in. For example, which ones are relevant? Which have higher priority? Which one you have to are time critical? Which ones are dangerous? Or which ones can be ignored? This is something that human beings do all the time, and human studies can show us actually by observing how human attention works and how disorders occur, and we can better understand that. I mean, the cocktail party effect, for example. If you're in a cocktail party and you hear your name, that may stand out to you, when normally it is just a lot of noise. In disorders like schizophrenia, there can be problems filtering filtering what you see. So studying these disorders actually can also potentially lead to how actually attention can work. Okay, so if you have figured out how to label the data, you know what to attend to, then what do you do with it? How do you do reasoning? Working memory, there's debate on this, but it's about 4 items, and sometimes it's modeled attractors. You can fuse input from sight and sound. For example, seeing a ball drop. You can associate these symbols in reasoning, and the causation becomes important. And learning causation actually can be both unconscious and unconscious. In working memory, it's conscious, but it's conditioning, it's unconscious. There's a lot of unconscious processing in the brain. And I would hypothesize that actually common sense is the learned constraints that we observe. That we can recognize anomalies, for example, just by seeing that they don't fit patterns. So what might be some applications for neurocognitive-inspired unsupervised learning? Well, one real application is understanding human cognition better, and disorders, that's important. But also potentially tools for intelligence augmentation, and things like robotic process automation, for example, that can work with you rather than just automating what you're doing. Patterns and sequences time series have been successful. Facebook is now working on unsupervised language translation, which you don't have a common set of sentences, you just have text. And there's now this techniques for mapping one set of text to another. And if we ever get to the point where we try to communicate with other species, that might be a way to do it. Concept formation, artificial creativity, and AI, AGI are all possible applications. Building on top of unsupervised learning with reinforcement learning. So I'm suggesting here that the future of AI will not be supervised, and really the problem with supervised deep learning is that we've already predefined what the classes are, and many of them are actually unknown and changing. And learning systems really need to self-organize and build models of the world to be really useful. And ethics in AI needs to look beyond just bias reduction, but also consider the causes. And cognitive tools for intelligence augmentation need to process like the brain in order to be seamless with them. And for that, explanations and causal inputs are key. And I just wanted to mention some of my collaborators when I was doing my PhD work that I did some simulations with various papers. And thank you for your attention.
Great, so we have a couple of minutes for questions. And I would actually like to ask, where do you see this field in 10 years? What do you think is the most, you mentioned some of the more practical implications of this. What are you most excited about?
I'm most excited about unsupervised learning. And building on top of that, actually looking at how the human brain works and using that to develop kind of a new generation of AI and IA.
Mm-hmm. Interesting.
Yeah.
Do we have any more questions? Okay. This one.
I wonder if you're familiar with Julia Pearl's work on causal inference. The reason, because last 20 years, because you mentioned causal inference, there's been a rise in those models, and what do you think about that and the future of how that will shape the landscape of unsupervised learning?
Yeah, I think it's very important. I didn't talk so much about it, but causal inference works when you have less data. When you get more and more data, it can start to get attractors, and that will give you more defined dynamics. So I think actually they can work together. Yes.
Thank you. I'm back here. Yes. So thank you for your talk. I saw one small fact that you presented. I found interesting, that we can spot 4 or keep track of 4 to plus minus 1 objects. Did that, I understand that correctly?
Yes, although some say 7. There's debate on that, but working memory is limited. Yes, 7. Yeah, there's the earlier work said there was 7 plus or minus 2, and the later work is claiming 4 plus or minus 1. I haven't done the experiments, but
So what would that mean, like, for organizing them? So if I'm being circled by 7 hyenas, will I blend 2 of them into one item? Or like if I'm playing soccer, like what does that mean? Is that for my mental map, or is that for my? Can you just elaborate a little bit what that actually means in practical terms? For our attention.
Okay. That's working memory. I mean, if you're for example, seeing what's in the scene, what you can track simultaneously, maybe looking at equations, number of variables, how they interact, how things interact in certain situations. So it's basically a way of being able to hold things in your memory and then understand the associations between them, and also potentially develop some sort of causal connection between those associations. The way they do the tests, I believe, is they do memory tests. They try to see how many things you can remember, and they give you distractors, and then they try to recall it. So I guess that's a limit of human cognition. I mean, it's possible that artificial systems could have a much larger working memory. And then what happens?
Okay, go ahead. Final question? Let's see where you come down.
I remember your name from the Cray system. I used to run terminal simulations on that 8H computer. I think I remember your name.
I worked as an application expert at PDC, the Supercomputer
PDC,
Center.
right.
Yeah.
But is your main interest the human brain or the artificial brain, so to speak?
Both, actually. I think they can inform each other. I think that maybe was what's missing. That our best example is human cognition, and we haven't utilized it so much because we don't really understand it. And if we understand it better, I think we can build much more artificial systems. But I also think that we don't have to automate everything. We can build tools, cognitive tools for extending intelligence as well.
Great. So if we don't have any more questions, I would like to thank you so much. Okay, so this was our final talk, and I just have a couple of things to say. Before that, at 9 o'clock we will announce the winner of the Toby competition. That light is so strong. Oh well. Okay, so at 9 o'clock we'll announce the winner of the Toby competition, so please stay. Until then, in Stockholm AI we also have a couple of upcoming events. We have a study group on recommender system.